So the next talk will be by Guang Zhang, a deep learning-based approach to moist physics parameterization.
Okay, let me turn on my share screen and see if it works. Okay, well, somehow looks like I'm not able to share the screen.
Okay. We can have overrides.
Yeah, can you put on your copy?
Sure.
We're getting ready to do it.
Would you like for me to?
I will get ready to share it in just a second.
Okay.
Okay, great. We can see it.
All right. Can you put on okay, full screen mode?
It should be in your view, I believe.
All the way down to the full screen mode. That's it. All right. Good morning, everyone. Sorry for the, well, in the East Coast, it's afternoon. Sorry for the hiccup here. And I'm going to talk about deep learning and trying to apply that to moist physics parameterization. This is what I've done with my collaborators, Yilin Han, Xiaomeng Huang, and Yang Wang. Next page, please. Next page. Oh, okay, good. All right, I get you. Okay, I guess, earlier someone has asked the questions, why deep learning? And in this case, particularly for parameterizations, there are many reasons, and I can come up with at least three. First, the conventional subgrid parameterization for convection clouds for GCMs are in deadlock. And over the past 50 years, we have made some progress, but no breakthroughs. Okay, second, the high resolution models, such as super parameterization and global cloud resolving models, they're good, but they're too expensive for long-term climate simulations. If you think of climate projection simulation, projections that's almost impossible at this current time, and probably unlikely in the next 5-10 years. And then the advances in computer science and AI algorithms and the big data have been have gone a long way, and we could make use of these advantages. Okay, next please. Okay, so I'm going to introduce a neural network that we used for the current work. And in the past, mostly of the neural networks used fully connected networks. Basically, each node in the prior layer is connected to every node in the next layer, etc. And one disadvantage of this is it has too many parameters, and it cannot go very deep. And so we tried to use a convolutional residual neural network, which is ResNet. With that, you have these input data like temperature, moisture profiles, and then you go through this ResNet, and then you produce some typical output, say like convective heating and drying, etc., and precipitation. And for the convolutional neural network, essentially, instead of connecting every node to the rest of the nodes in the next layer, we only select a few sparsely connected nodes and link them to the next layer. That way, the number of parameters is substantially reduced. Okay, next. So for the training data, we used 1 full year of SPCAM simulation, and the output is every time step, which is 20 minutes. And then we run the SPCAM for another year and use that as independent data test data for the trained network. And we randomly selected 800 grid points for the training. So we have a total of about 20 million profiles for training. And the figure shown below just shows the number of data points we used. And this only shows 200. And we have 800 randomly. And even with that, it's about 5% of the data points every time step. Okay. So the training data is 20 million, and the evaluation data is like 360 million data points. Okay, next. Okay, so I'm going to give a little bit more information and details as to the neural network. Okay. We have a 22-layer neural network I mentioned earlier for the fully connected networks, and most of the previous studies use 10 layers, which is probably as deep as you can go with fully connected networks. And for this network, we use 22 layers, and so we have first we have the input, and then we do a convolution, and then after that, we have 10 res units, which each contains 2 convolutional layers. And then after that, we output, we go through one more convolution and then put the output. The number of input profiles we have is 36. And so that's a lot compared to conventional parameterization. We have like maybe temperature, moisture profiles, and then a couple more. And even that, we collapse them into a scalar like convective instability or CAPE or large-scale forcing. So there are only a few input variables, and here we use 36. And for neural networks, it doesn't know the physical laws. So we have to give some constraint. And one constraint we use is moisture static energy conservation. And we use that as a penalty term so that the output would satisfy the energy conservation. Next, please. Okay. So much for the network, and then next I'm going to show you some of the results. And this is annual mean precipitation from the evaluation data. The top is SPCAM simulated the evaluation, simulated the 1 4-year data, and the middle is neural network produced, and the difference is at the bottom to visually, to have a better visual effect, the difference is amplified by a factor of 10. So anything you see that is about 1/10 of the scale of the actual value. And in general, the difference is less than 5% at any single location. Next, please. And then this on the left is convective heating, or well, the moisture physics heating. And again, top is SPCAM simulation, middle is from the neural network, and the bottom is a difference. Again, difference is about the error is slightly larger, but still it's much smaller than the actual value, again, about 10%. Okay, next, please. Right, that we also included the cloud water and cloud ice as predicted variables. And here, they are even smaller, about 1%. Latitude cross sections. Okay, next. Okay, so we have this ResNet, and we also looked at a number of other networks and compared it to them to sort of perform some kind of sensitivity test. I forgot to mention that among these 36 profiles, we included the connected memory. That is, in addition to the current time step, we also included the history of the connection in it. And so in the left, we tested how much of the history can be included to bump up the accuracy. And it turns out that we only need to include maybe 2 or 3 time slides, which is about an hour or so. So the connected memory has about an hour value. And then we compared it to the fully connected network, which is DNN. We tested this with 10 layers, which is typically what the others use. And the errors are about twice as much as what we get with residual network. And then we further increase DNN to 22 layers, which we know that is not going to work. The errors run up to like 15 times. And so for 22 layers, the residual architecture does not fully utilize its take full advantage of that. And we try to further increase the neural network. By the time we get to 30 or 40 layers, which it does show a substantial advantage. Okay, next. Okay, then we tried to do a single column model test. And in this case, we used the SGP side, and the precipitation time series is simulated quite well with both control arm and with a neural network. And at the bottom shows the time series, the convective heating and the drawing. Again, the neural network is the one at in the middle, and you can see that it captures observational time series at the top quite well. And next. Next slide. Yeah, and then we put it into a prognostic mode. In the past, in the evaluation, it's really diagnostic, and the SGP will also run the diagnostic test. And here for the TWPIs, we tested it in full prognostic mode. That is, the heating and the drawing profiles coming from the neural network goes into the model to participate in integration. We tested it with all 26 days, and here we only show the active monsoon time period. And again, you can see that it captures the convection events quite well. Okay, next. Okay, so the challenge, however, is to put it into 4GCM and replace the conventional convection and cloud parameterizations. And next, please. So we tried that, and here the top panel is offline test, and the bottom is from the SPCAM simulation, and then the middle is online simulation. We tested, looked at the first 5 days, and the next 10 days, and the next 15 days, and the next 20 days. You can see that if you look at the different, the images between the middle and the lower panels, there are fairly similar. However, when we integrate further, we were able to run that for as long as 3 months, and it didn't blow up. So we could have still continued to run. But the simulation gets drifts away very bad, and so we shut it off. So in this sense, we are able to run up to 3 months, but the realistically we probably expected to have probably up to a month. Okay, so next. So this is a summary of my talk. First, we developed a moisture physics parameterization based on neural ResNet, and it emulates the SPCAM simulations very accurately. And compared to the fully connected neural network, which is about typically about 10 layers, our network is much deeper. In the presentation here, it's 22 layers, and recently we tried to make it even deeper, up to 40 layers. Yeah. And then, however, when implemented into the CAM5 simulation to replace the conventional parameterizations, the simulation drifts away after about 2 months. So there is much more work to be needed in the future. Thank you.